Good afternoon, everybody. Welcome to the fifth NAIR Pilot Researcher Showcase, Empowering AI Research Innovation, organized by NAIR Pilot User Experience Working Group. I'm Nitin Sukija. I'll be your host for next 1 hour. And I would like to thank you all for joining us for this webinar and also our panelists and speakers who have given valuable time and their contribution to NAIR Pilot to join us. With that, I will introduce our panelists. So we have Dr. Krishna Kant, Dr. Shing Chang, and Dr. Anna Lučić, who will be presenting today. I'm going to talk about Dr. Krishna Kant, who is a professor in the Computer and Information Science Department at Temple University in Philadelphia, PA. He is also an IEEE Fellow and an IEEE Distinguished Visitor. Prior to joining Temple in 2014, he was a research professor in the Center for Secure Information Systems at George Mason University in Fairfax, Virginia. From 2008 to 13, he served as the program director at the National Science Foundation, where he managed the computer systems program and co-led the development running of an NSF-wide sustainability initiative called SEAS. Prior to NSF, he spent 22 years in industry, including the server division of Intel Corporation and telecommunications standards division of Bellcore, now Ericsson. Before 1991, he was an associate professor of computer science at Penn State University and assistant professor at Northwestern University. He received his PhD in mathematical sciences from University of Texas, Dallas in 1981. He has published in a wide variety of areas in computer science with current interest in largely centered around computer vision, multimodal LLMs, misconfiguration diagnosis, enterprise networks, intra-body networks, and storage systems. He has authored a graduate textbook on performance modeling of human systems and co-edited several other books. With that, I would like to invite Dr. Kant to share his screen and start his presentation.
Okay, thank you. And let me start sharing this screen. Okay, can you all see the screen?
Yes, we do.
All right.
Give me
Okay,
full
so
screen.
thank you for the introduction. I will be talking about integrating.
Dr. Kant, it's not full screen. Can you make it full screen, please?
Oh, sure.
Wait.
Okay, so I will be talking about today integrating AI and in particular the vision language models and LLMs with logic reasoning. And this is an IRR project which was funded about 2 years ago. Okay, so let me get started. So the theme of our work essentially is to enhance the accuracy and comprehensiveness of the VLMs, and also find a way of justifying what is being described, for example, an image or a video. So in terms of what reasoning means, well, originally we started out with logic reasoning using what is known as MT, satisfiability modulo theories. It's a method of having a set of axioms, and from there you derive some conclusions. So it's a fairly formal reasoning, and this, of course, involves the basic axioms of logic, plus it can be extended in multiple ways with domain-specific knowledge so that you can make fairly comprehensive conclusions from there. Nowadays, of course, you're all aware that LLMs can also do some level of reasoning, although there is some controversy about that, and that could also be integrated in this. Okay, so we looked at a number of specific use cases. So one is that if you can integrate the vision language models with your traditional computer vision methods, then you can do a much better job than either or, essentially. So that's sort of the idea, and the glue there is the logic reason. And I'll show you some examples of that. What it does is it allows you to come up with a sort of a justification mechanism fairly easily. We also looked at, or still looking at, actually on another NSF project, student engagement from videos in a classroom. And then also going a little bit deeper into that and worrying about the differences between the expressed emotions and the experienced emotions. That's getting a little bit into psychology. And then we have also some extended use cases, which are not necessarily VLM specific. They go more generally into the LLM category. And those are in the area of fault diagnosis in enterprise systems. So I'll show you an example of that as well. So in terms of the resources, we mainly need the GPUs, and we have used the H100s, the A100s, and the Intel PVC at Tamu. The main software that we use is PyTorch. And we've used VLMs like MiniGPT-4, which is very popular in academia. We've also used Video Llama, which is more resource hungry than MiniGPT. And we have also used a bunch of LLMs. So in terms of just to talk a little bit about the challenges, and initially when we came online, there was a lot of startup delays and problems to get going in terms of being able to use the system. We had all sorts of errors that we encountered. And we had multiple meetings with Zenhua, who really was extremely helpful in terms of resolving all those problems. And ultimately, we were able to use the infrastructure quite effectively. Now, in terms of the kind of work that I was describing, the main limitation is not really the CPU or the GPU computing power, it is the memory. Because these large language models, particularly the vision language models, they do require a huge amount of memory. In fact, we have local computing facilities with 2 GPUs, each with 48 gigabytes of memory, and we routinely kind of run out of memory. So memory is the big limitation for us. Now, in terms of the community engagement, well, I definitely like the idea of knowing what people are doing with VLMs and LLMs, and which is, of course, a very hot topic these days, and all the different ways in which they are being used. And I believe that this kind of webinar is a good way to learn about what others are doing as well. Okay, so with that, I will go into some specifics a little bit. Okay, so the first thing is that the integration of the VLMs with your traditional computer vision techniques. So VLMs are actually really good, and they keep getting better and better in terms of describing overall what's happening in an image or in a video. So for example, if you give the top picture to a VLM, it will easily be able to describe what's going on, even from a single image. And similarly, the one at the bottom. However, where these VLMs have problems is when you get down to low-level details. For example, the precise locations of people, their attributes, or their movements, and things like that. And often in some applications, for example, in situational awareness kind of applications, you want to know not only what's happening at a high level, you also want to know at a sort of a more finer grain level that's what's going on. So that's one reason to try to integrate the two together. And that's what we have done. And what a outcome or something that falls out of that is that we also have a mechanism by which we can justify the output. And the way we essentially do that is by trying to look for consistency between different types of descriptions. So for example, here's one thing that we did. So you have a traffic on the highway, and what we are really interested in is trying to find accidents and the type of accidents or near accidents. So instead of using simply a VLM to detect these accidents, we can use two VLMs, and which recognize different but related activities. And we can also use our traditional computer vision to recognize simpler aspects, how close one vehicle is to another and things of that nature. And what that can be used for is it can be used to determine where the weaknesses are, and therefore, when we are trying to do the fine-tuning of VLMs, we can do a significantly better job. And the chart here basically shows that by using this mechanism, we can get a significantly better accuracy in the final fine-tuned VLM with the same number of videos or images for training or fine-tuning rather. So the main thing that we focus here is on the consistency between different descriptions, and there could be consistencies between various types of aspects of the same image. For example, if you're looking at an accident, what happens just before the accident, and whether that's consistent with the accident itself. For example, in case of Taekwondo, the two things you might want to correlate is the hand movements versus the leg movements. Or you could decompose the activity into sub-activities or look at the alternate activity. And by looking at this consistency of this, we can not only do a better job of tuning, but we can also keep this during the inference time and have a mechanism by which you can say, yeah, things are consistent, therefore we have a little more confidence, or things are not consistent, and therefore we don't have enough confidence in this result. Okay, how am I doing on time?
You're good.
Okay.
5 minutes, yeah.
Okay. So there are two other areas that I want to talk very briefly about. One is the student engagement. And here, basically, in addition to using the VLM to determine whether the student is engaged or not, we can also look at the input from the humans. Humans have often preferred or dispreferred responses, and we can integrate those to get a significantly better results as shown here. There's another one, which is where we try to distinguish between expressed and experienced emotions. So VLMs mostly look at the faces, and therefore they look at the expressed emotions. Now, the experienced emotions actually are more related to the physiological measures like the heart rate or the breath rate. And it turns out that you can actually determine heart rate and breath rate through the videos themselves. But then to get a real accuracy, you need to integrate them explicitly, just assuming that, okay, the video VLM is already looking at the video and therefore it should have that information. That's not enough. And we can get a significant bump in the accuracy by explicitly integrating that information. And also, we can look at essentially consistency across the different images in a video. And if things are consistent, then you basically get better accuracy. And then finally, about the diagnosis. So this is a very different application. We want to do an online diagnosis of faults based upon the complaints that a user is making. And the users originally have complaints which could be rather vague. And then we use LLMs to basically probe them further and find out what exactly are they talking about, and prepare some sort of a trouble ticket. And then we use a combination of both the LLM and a classical, not really classical, but a traditional type of algorithm to do a much better job than you would be able to do otherwise. So here's an example. So this is an algorithm that we developed, ConfX. It takes total of 30 tests, but if you integrate it with AI, you need only 18 tests. Now, in terms of how you integrate it, well, the AI agent might suggest certain tests, and then we have some tests that we determine, and the question is which ones you should run first. So, for example, in case of A, you run the test that the AI agent suggests, then you run the tests which are in the intersection of our determined test and the AI agent test, and then finally, if necessary, use the test that we have figured out. And that works quite well, as you can see here. This other strategy where you run the systems only test and then the intersection, and that also works very well. So by doing this integration, you can see that we can significantly reduce the number of tests. And in all of these cases, of course, we do much better than the experts. So on the top, you have the number of tests that the experts took, actually, in terms of diagnosing the problem. So we can certainly do much better. So those are all the cases I have. So in conclusion, basically, we can achieve better accuracies by integrating LLM or VLM-based methods with the traditional methods. And to do that, it requires some reasoning methods, which is what we are focusing on, we have used successfully. And that's all I have.
Thank you, Dr. Kant. We are on time also. I don't see any question for you for now. If you have any question, Dr. Kant, please put in the Q&A section. With that, I would like to thank Dr. Kant for his presentation and contribution. We'll move on to the next presenter. Next panelist is Dr. Shing Chang. He is a professor and acting department head in the Department of Industrial and Manufacturing Systems Engineering at Kansas State University. He teaches courses related to quality engineering and big data analytics at both undergraduate and graduate levels. Dr. Chang earned his PhD degree in industrial and system engineering from ISC at Ohio State University in 1991. His research interests include smart system monitoring, profile monitoring, statistical process control implementation for big data applications, neural networks, and fuzzy set applications in quality engineering, spatial data modeling, and multivariate data modeling and visualization. He's a senior member of IASE and ASQ. He received the SME Outstanding Young Manufacturing Engineering Award in 1997 while serving as the president of the QCRE division of IISE. He was a department editor of Online Quality Engineering in IIE Transaction in 2022 to 2025. And you can find his scholarly publications all over the web. With that, I would like to invite Dr. Chang to share his screen, in which we see. It's all yours, Dr. Chang. Thank you.
Thank you for the organizer for the invitation. So as you can see, I'm not a computer scientist. And the area I started with the research in AI related to is neural network control chart. That was the early 90s. That's when they get started. But at that time, the power of a neural network model is not as good as a traditional statistical model. Not until the ChatGPT moment in 2022. Now you have an explosion of the AI power. So my interest is to how do I integrate that content to modernize my courses. So when this NAIRR pilot program come along, it become an immediate interest. So I want to tap into the resources we have and then try to get into this area. Let me see if I can move that. Now, my research area is in quality monitoring So basically, all the technique is statistical based. And you take on the small samples because we cannot take on the large data. And then because it's a time series data, you just take the data points at any time, you make the assumptions about the distribution, and you try to make sure the sample meets the distribution assumptions. But now, neural network, generative AI opened another door. So I think a lot of you out there, like me, will never learn about the neural network when we go through our schooling. So we have to learn on the fly. So today I'm going to talk about how I approach the problem. How do I introduce the content into the classroom? So for me, over the years, mainly dabble into this field is about how do you take the quality characteristic and then make sure there is a distribution. So it has a univariate, we expand it to the multivariate, and then we eventually adventure to the images. But the question is still the same. Does the data, in this case, the image, fit into what you expect it to be? And then can we use AI to solve that? And so over the years, I've been accruing different user case. For example, 3D printing. You can take an image of the layer after it prints, and then you go against your existing data sets. You try to determine is it good or is it not good. So it's like in a language of machine learning, it's a binary classification problem. But then when the transformer comes along, all of a sudden you can infer just like a sentence to the processes maybe several layers before. So you open the door for a lot of possibilities. So that's what I would like to do in my advanced quality engineering practices. And then I think this pilot program will enable students to leverage the resources which otherwise not available, and to use it to advance the field. So in my proposal, I say, okay, could I use some NVIDIA processor, because from the outsider, this is what we heard. Okay, NVIDIA is the best, and then we're gonna use it. But eventually, we got approved for this is Indiana University has a JetStream 2, and out of the list, that was last year. There's the choices were very, very limited, but now I saw a lot more was available. But this is the one that we proposed. My students, when we first come up with this, and this is the final SU we spent. But I look back to my proposal. This is only 4,000 SU we propose. So we use 100 times more than we requested it. But fortunately, this is the new proposal. We assume, okay, what if I can scale up to 20 students? How much should I estimate it? So this is our estimation. So this is one of the things that, to me, the outsider, very difficult for me. Even for students, really, they don't know. They just run. They have a model. They run it. They try it out, and then they have no prior knowledge of how much resources they need. If it is free resources, like they use the Google product, Colab, and most likely when they run to a certain step, they will put in queue. They're not going to proceed anymore. So when we get into those experiences, I think I really think we need some kind of admin support. But for the JetStream 2, they just provide the environment. So as a user, we have to provide all the admin supports, like user management, and then who's going to sign up the assets. So there's a lot of chores. I don't think as an average user, maybe for the computer science folks, you already have your admin, but for the people like me trying to teach a new subject in this field is very difficult. We like to, so once we use 100 times more, the staff from the jet stream 2 came back and say, hey, can you do a supplement? I said, yes, we can do that, but they never told us where to apply for the supplements. So this is the where I think the pilot program and the resource manager may have a better communication. So I don't think the jet stream 2 staff know where to do it. They know we need to have supplement, and I don't know where to have the supplement. So there's some kind of a disconnect in that application process. So there's a wish list for the people who are interested in applying for a grant. I was told that there's a lot more research grant. It turns out at the same time, I have another research. The idea here is that can we train a multimodal model that is small enough to put on the mobile phone that will intercept the scammer's call, so the elderly won't fall for it. So it's a kind of preventive kind of app. So when we put into this proposal, and then we say, okay, we just put on the same old NVIDIA resources. But I got my grant, my teaching grant, but my research grant, I never heard from them. And then I went to the DC for the first conference, and I was able to talk to the program manager, and then it turned out to be it's a mismatch. And then there is multiple tables from various different resource vendor. So I set into the NVIDIA tables. It turns out for us to get the grant, we need to have a very, very large model that require the training to be like a 30 days straight, and then it's a huge model, and scientific or otherwise, and then for that to be granted, because very limited resources, and so we need to justify how large. But that message was never conveyed very clearly. I think they are doing a better job now, but I wish at the time I know a little bit more about the resources. So that's the feedback I told them. So hopefully moving forward, you will have the opportunity. I think this forum also provide a case, the user case for those people who want to get into the field and then be able to leverage the best resource. Actually, it's a matching problem. So I think the team now try to match the best they can for those resources. But when you write a grant, I think it's easier if you know what you wanted to have. You know? So why is that a mistake? I will just talk about that. Already talk about that. Okay. I think there's also a way you can minimize the resources. So you can use a foundation model only trained on the additional layers. Then you don't have to train from the scratch. That will probably save you a lot of resources. I think moving forward, there will be a lot of those foundation model coming online and become a public domain. So another one is I just talk about users management. So it's from the student point of view, hey, we have these free resources. I can run as much as I can. Just they run, and then they just, student make mistakes. They have to rerun it. That's a few days. You use a lot of resources. So there's I think there's a room for improvement that can benefit all parties. And also, I wish there's a more public data sharing for teaching purposes. I also teach big data, so I learned if you can download the data sets in your computer and try to run it, it's not big enough. So basically, for all the resources for teaching purpose, I wish they have some kind of public data sets that sit in the resources. So we don't try to move the data, but we use the data to use the data leverage and train on the model. And then that would save a lot of time. It is impossible to really download the data in the local and then try to run with it. And then this will be the same for all the classes. So I think last time I was in the conference, people talk about that. I think there's some working group out there, and I'm anxious to see how they come up with those sharings. I think most of the national lab, they want to share their data, but their data is sitting in their servers. So it's not sitting in the resources server. So that's another disconnect that we need some improvements. And then also the projects. So is there a platform? Once we run this student project, there's a way to disseminate that result as well. So I mentioned about the foundation model. So my class, my student trained on this neural net. We spend a lot of computational resources. We'd be more than happy to share what we already trained. So the future student can take that and run with it and add more and then revise it. So there's a lot of room, I think, we can leverage, and then we can improve in that realm. So let me give you a couple of examples. In the classes I taught that I use a neural net. So this is the easiest, okay? This is the traditional neural network. And then, so I have my student go to using TensorFlow in the Colab. And then they can specify typically a T4, P100, they can just choose. And then if they run a long time, then maybe they will put back in the queue. So sometimes when it's very, very busy, like after dinner, it's very difficult to get on. I also run another free platform. It's called Databricks. Some of you probably use it. They have a free community editions. But when I first used it a few years ago, it's pretty good. But now in recent years, students told me that sometimes they cannot even log in because there's too much usage. So that's why this grant will help students a lot, because they have it's a more captive group of students that can make this better. So another class I teach, this is more of a topic course. So I want students to pick on any one of those areas. I really don't have the time to cover them all. So what I did was we just talk about the basic of the neural network, they're supposed to be. And then I set them free. I just say, okay, let's use this book. This book happened to has a sandbox. So you install, everything is inside the sandbox. It's easy for you to run. So once they learn the subjects, the example I gave you is a diffusion model. So I want them to be able to use a small number of samples, and was able to kind of expand it to other areas. Then they can pick any one of those subjects and then pick their data sets and their application, and then use the same model to run with it. And it turned out to be a successful experience for a lot of the students. And then at the end of the semester, they all presented their project, since they already run their portion of it, so they can appreciate the effort going to each one of those areas. So that's a final project I required them, and then that's where one student run 100 times more than what I asked for. Okay, so with that, I'd like to see if there's any questions.
Thank you, Dr. Chang. I do not see any questions for you right now. If anybody has a question, please put down for Q&A. I have one question for you, Dr. Chang, since we have time for,
Sure.
How do we replicate your work with respect to students, which you're doing with undergraduate or graduate, if we want to apply same in our colleges?
So because every field is kind of different. So I'm just kind of think. So first of all, we have to learn ourselves to beef up our knowledge, and then so it's like a co-learning group. So we learn and then we teach each other. So that's I'm talking about a framework, okay? And then once we learn the subject, and then we learn the subject area, then we learn the AI, and then we try to kind of marry those two together. And this has happened in a topic course.
Okay. Thank you. Thanks, Dr. Chang. With that, I think I would like to thank you again for your valuable contribution and your suggestions. We're going to move on to our next presenter, Dr. Anna Lučić. I'm sorry if I messed up the name. I hope I'm right.
Yes.
Anna Lučić is a research scientist with the Applied Research and Technology Group at the Coordinated Science Laboratory at the University of Illinois, Urbana-Champaign, where she also serves as Assistant Director for Data Management with the Artificial Intelligence for Future Agriculture Resilience, Management and Sustainability, AI Farms Institute. Her work bridges socio-technical data analytics, natural language processing, computer vision, with a focus on advancing data model alignment, multimodal AI evaluation, and metadata-driven interoperability. With that, Anna, I will ask you to share your screen. If you can unshare your screen, Dr. Chang, then it will be great, please. Thank you.
Thank you. Thank you for that introduction.
Yeah, good.
Okay. Yeah, thank you for the introduction. I will present the project, and thank you for the opportunity to present my work on the NAIR project thus far. So I'm calling this work Multimodal Vision Language Model Evaluation. This is a teamwork. I am only one of the persons that's working on it. Other people are also Garvita Alabadi and Sarah Gott. So I will start with what are the research questions that prompted this project and how did it start? This project is guided by the question how well visual language models can identify agricultural species. As we heard in the presentation earlier, visual language models can be very good at high level knowledge, but they may not be as good with low level details. And why agricultural species? This is coming from my affiliation with the AI Farms Institute, which is one of the AI nationally funded and agricultural focused institutes in the country. We were interested in how well can they recognize finer grade elements such as interactions, behavior, ripeness of the plant, or secondary objects in the visual collections. And also another question behind this work is to what extent VLMs can be used for generating additional supplemental metadata for the existing images and video collections. So when I say additional and supplemental metadata, what do I mean? I mean like background, lighting, time of day, indoor, outdoor differentiation. You may wonder why is this needed and how this can be helpful. This additional metadata can be helpful with respect to linking data and also linking data with other research artifacts such as models, because I come from the data management background and I see a lot of data sets and models that can benefit from additional metadata. And I feel that like a lot of research artifacts could benefit from it. And benefit in terms of like that we could better link the resources. I know that AI models have wonderful capabilities, but I think that this can only assist the AI models with linking resources and make, possibly drawing richer signal from such linked resources. So you may also wonder, like, what is the practical scenario for this type of work, like where we want to see, like, to what extent visual language model or state-of-the-art visual language models can recognize agricultural species. So one practical scenario would be a farmer interested in monitoring their field. And so some of the questions that a farmer may have is like, have foxes visited the field? And if so, how often have they visited? Also, have birds visited the field? And if so, can the birds be identified? So because there's lots of types of birds, so can we say like, like which birds have visited? Is it crows? Is it some other types? Also, I know that from my work with the AI Farms Institute, I know that predators can be visiting the field, but they can also be a threat to the livestock. So, like, a farmer could potentially be interested in like have wolves or deer or groundhogs or coyotes or foxes or bobcats visited the field, and at what time of the day or in what manner, and so on. I mean, would a fence be helpful, and so on. So as we know, cameras do not reason by themselves, but if they can be coupled with a system that can recognize actions and behaviors, they can be of much more value to the farmers. So, so this is the kind of like the motivation that prompted this work. And so what did we do? We decided to create an agricultural data set. And there are lots of benchmarks out there. However, we did not find one, we may have missed it, but we did not find one that was particularly kind of like suited for our purpose, which is often the case when you are starting some work. So we have identified publicly available data sets that allow modification and further redistribution of images. And we have also prioritized data sets where species have already been delineated with bounding boxes or other type of segmentation. And so these data sets are available publicly. They are either available through the GitHub or through some data repositories. Some of them we have used in the past, some of them are new. And basically, thus far, this is still a work in progress. Thus far, we have like 23 animal species, and sometimes they are camera trap images, sometimes they are image collections that have like basically one species of typically one, species identified in them. And then we have 23 data sets that feature plants. They can be fruits, commodity plants. There can be leafy greens, and we have 50 pests. So this is the number of images that we are working with. As I said, this is a work in progress, and we will be adding to this data set. So you may wonder, like, what are the species in this agricultural data set? And this was actually created by ChatGPT 5.0, these infographics of plants, animals, and pests. So this is just a sample. As I said, we have 23. So these are the sample of plants. We have them from the real fields. They are images of apples from the orchard, or avocados or celery in the field, almonds, beets, carrots, but this is only a sample. We have animals such as pigs and goats and crows and woodchucks and chicken and red fox, and we have some agricultural pests. Yes. So what are the models that we have used? And what are the cloud platforms? This work would not be possible without the access to the computational resources, which is thanks to the NAIR project. So we have used, we had access to GPT 4.5 model through the Cloud Bank resource and also through the Microsoft Azure, and then through the Microsoft Azure platform, we had access to the OpenAI GPT 4.5 and GPT 4.0. We also, through the Samba Nova systems, we also had access to the Llama 4 Maverick 17B 128E in instruct model. These are the resources that this project has used, and they were very helpful because these are some of the state-of-the-art models. We were just trying to see, what is the extent and what is the accuracy with which these models recognize these agricultural species. And as you know, prompt definition is very important when working with these models. So this took a little bit of time, how to actually come up with a prompt that would work well. And we were actually able to come up with a prompt that would give us a JSON response. And so we could get a structured response, which is very helpful. And this is the prompt that we gave to each of these three models. And we were wondering, analyze this image and provide a JSON response with the following structure. And so primary focus, general environment, general lighting conditions, weather conditions, general time of day, description of the background elements. These are very important elements of the visual collections that can help with a number of tasks. We also have a prompt continuation. This is a pretty large prompt. And, list the primary visible objects, list the secondary objects, location, action, interaction, technical details of the image, and some meta details. We also try to emphasize through the prompt, use unclear or not visible for uncertain elements. And so this is the prompt that guided the extraction of the data from these models given these images. And so these are the evaluation results. So as I said, we had 23 animal species. And out of that, we had 5,568 common images, which were analyzed across 23 species, because not every model was able to, not every image passed through every model. You can imagine that it's not always so perfect. So and I will talk about this a little bit later on, but in general, we managed, 5,568 images passed through all three models. And so as we can see here, GPT 4.5 traditional accuracy, which means I had to use hierarchical evaluation because sometimes the models might give higher order from the taxonomy, which is also correct. But in terms of what is the common name of these animals, and can the VLMs recognize the common name? As we can see here, GPT 4.5, the traditional accuracy was 90%. Genus level accuracy, this is a level higher. This was only 10%. But this is probably not that important because the traditional accuracy is 90%, which is pretty good, which is actually very good. GPT 4.0 also had 90% accuracy. Llama 4 Maverick had 70% accuracy. So we see here that this is an overall good accuracy. We also found what were the challenging species. Those were like groundhogs, bobcat, and this is probably because of their similarity to other animal species. Yes, and so in terms of like plant species evaluation results, we had a little bit bigger pool of images. We had actually 17,915 images that were analyzed across all 3 models. And again, we had 23 species. And so these are the results. So GPT 4.5, in terms of traditional accuracy, this was 31.71%, but the genus level accuracy for some reason was 43.6. I'm still looking into that. And GPT 4.0, it was 28.74%, and the genus level accuracy was much smaller. And Llama 4 Maverick was kind of similar to GPT 4.0, and it was 24.4%. So why is this interesting? So we see here that these plants that have kind of like a clear shape and form, such as apples, avocados, grapes, oranges, they are identified with a high level of accuracy. What we also see is that medium difficulty plants are peppers, tomatoes, and raspberries. We see that they are all red. And we can see that depending on the scale of the image or on the distance, like some of this could be confused. But then we also see that what is the most challenging was the leafy greens, because they are all very similar, such as like celery and leafy greens and romaine lettuce. So we have identified a kind of like a gap where probably some additional fine-tuning could be helpful, and where we know, like if we wanted to use it for building of an application, we should probably pay attention to the area of leafy greens. Yeah. And then finally, pest evaluation results. We only had 50. I mean, there are lots of pests. We will be adding more, but thus far we only evaluated 50 species, and then these are the results. So GPT 4.5 had 60.9% traditional accuracy, which means that they were able to recognize the common name of these pests. GPT 4.0, it was 57.1, pretty similar to GPT 4.5. And Llama 4 Maverick was 48.6. And so we see here on this infographic, which was also created by ChatGPT 5.0, we see like what are the easier identification. We also see like, a more clear color pattern and maybe shape pattern, but then we see like what are these different types of ants are definitely harder to recognize, I think, for humans, but also for AI models. So I hope I'm doing well on time. And so what are some of the obstacles that were encountered? Yes, am I okay on time? Yeah, okay. So what are some of the obstacles that were encountered? So as you know, I mean, it is wonderful that Microsoft Azure has like content filtering. This is very kind of like a guardrails. This is very much necessary and needed. But I didn't know how to bypass those, because some of the images were filtered, and they showed that they were violent images, but I am kind of like looking at this image and I'm not sure like what is particularly violent in this image. And so I didn't know how to bypass this. And so some of the images, like this is the reason why some of them were not processed. And also like another kind of like issue that we have is that we did have a ground truth for the main species in the images, but we don't have ground truth data to evaluate for like background and time of day and weather and also additional species. So this is a problem that we are currently tackling. And And then in terms of the other goal, it's like, this is basically what we will be trying to do. We will be trying to enhance the metadata of the visual collections with additional metadata that is provided by the visual language models. And this is what this would look like. We would have some ground truths, but we would also have VLM-generated metadata. So this is another goal that we are currently working towards. We will be also expanding this data set and releasing it with augmented metadata. And so this will be a publicly available resource. So I think this is all I have. Thank you for listening, and I'll be happy to take any questions.
Thank you, Dr. Lučić. I don't see any questions. With that, I think we are only left with 2 minutes, but I think I can take time to thank you all. Thank Dr. Lučić, Kant, and Dr. Chang for giving up your time. I know it's semester, you're busy. And like I said, I think we will post the videos online, and hopefully everybody else can take advantage of your contributions. I would like to also thank organizers, Romanella is there on the call, and all the other members of the NAIR Pilot User Working Group who are organizing these events, and also the audience who are here actually trying to learn more about NAIR Pilot. With that, I will conclude the seminar. And again, thank you all for joining us. Thank you. Bye-bye.
Thank you.
Thank you.